Welcome. This video is on 7.3, Diagonalization. Okay. First of all, we needed a definition. So let's start off with two n by n matrices. So let's let A and B be n by n matrices. We say that A is similar to B. I should underline all of it. This is what it means for two matrices to be similar, okay? We say that A is similar to B if there exists an invertible matrix S such that B is equal to S inverse AS. Okay, so this is what it means for A to be similar to B. Okay, before we move on, I want you to notice the symmetry of this definition, okay? Note, if A is similar to B, B must also be similar to A, since if B is equal to S inverse AS, then what does this mean? Well, if I multiply both sides on the left by S and both sides on the right by S inverse, then this means that A is actually equal to S B S inverse, which is the same as S inverse inverse B and then S inverse, right? And so you could see that it takes on the exact same form, okay? But this is the key relationship. The key relationship is right here. This is what it means for two matrices to be similar. Okay, so why do we care? Well, we have a very important theorem here. Similar matrices have the same eigenvalues. And this is including multiplicities. This is a really cool theorem, so let's go ahead and prove this. We want to show that similar matrices have the same eigenvalues, right? So let's write down the proof. Remember, we are assuming that they're similar, right? So let's go ahead and write that down. So suppose B is equal to S inverse AS for some invertible matrix S. Okay, so we want to figure out if B and A have the same eigenvalues. What we're actually going to do is show that they have the same characteristic polynomial. So what is P of lambda for B? Remember, this is the determinant of B minus lambda times the identity, right? But this is equal to the determinant of S inverse AS minus lambda times the identity. Now the trick is to write I, the identity, as S inverse times S, right? Isn't this the same as S inverse S? That certainly makes the identity. So this is going to be the same as the determinant of S inverse AS minus lambda times S inverse S. Now here's the trick. The trick is to factor an S inverse out on the left. I can do that over lambda because lambda is just a scalar. So this is equal to the determinant of, if I factor an S inverse out, let's see what we get. Oh, and I can also factor an S on the right. So here's what we get. Right? There's an S that comes out on the right on both, and there's an S inverse that comes out on the left on both. But then this is equal to the determinant of S inverse times the determinant of A minus lambda I times the determinant of S. This is just rule of determinants. And we also know that the determinant of S inverse is 1 over the determinant of S. So we know that this and this multiply to 1. So what did we just show? We just showed that P of lambda for B is the same as P of lambda for A, because look what we have left, just the characteristic polynomial for A. Okay, so we just showed that similar matrices must have the same eigenvalues with multiplicity because they actually have the same characteristic polynomial. Okay. All right, so let's continue the discussion. Suppose an n by n matrix has eigenvalues lambda 1 to lambda n. Then the simplest matrix or 1 second here, let me write that a little neater. The simplest matrix with the same eigenvalues is what? Is the diagonal matrix. What do you do with the diagonal matrix? What you do is you just put the eigenvalues on the diagonal. So the way we notate that is like this. Lambda 1 to lambda n. What does that look like? It just looks like this. Lambda 1, lambda 2, lambda n. Everywhere else is a 0, right? This is what we're talking about. Okay, I'm hoping that it's easy for you guys to see that this guy has this, the same eigenvalues, right? The eigenvalues of a diagonal matrix is just the diagonal elements, right? Because what would the determinant of d minus lambda I be? It would just be the determinant of lambda 1 minus lambda, lambda 2 minus lambda, lambda n minus lambda. Everywhere else is a 0. But the determinant of a diagonal matrix is just going to be that. So it's easy to see what the eigenvalues of this matrix are going to be, right? It's just going to be lambda 1 to lambda n. Okay? So we know that the simplest matrix with the same eigenvalues is a diagonal, so a natural question arises. When is a matrix A similar to a diagonal matrix? Okay, this is the idea. The idea here is if a matrix is similar to a diagonal matrix, then that means it's possible to find the eigenvalues much easier. Okay? So this is a theorem that answers this question, okay? An n by n matrix A is similar to a diagonal matrix if and only if A is non-defective. So that's the first thing. The first thing is that it is similar to a diagonal matrix if it's non-defective. But what will that diagonal matrix be? And how do you find it? So this is actually the second part of the theorem. So if so, and if lambda 1 all the way to lambda n are the eigenvalues, and it's important to state that they don't have to be distinct eigenvalues, right? If you recall, a matrix is non-defective if it has n linearly independent eigenvectors. It doesn't have to have n different eigenvalues, okay? We just know that it has enough eigenvectors, right? It has n of them. So let's suppose that lambda 1 to lambda n are the eigenvalues, and some of them might be repeated. And we're going to say that these guys have the corresponding linearly independent eigenvectors. V1, V2, all the way to Vn. These are different, and not only different, but they are linearly independent. Then, if S, and this is the trick here, the trick is to create a matrix of eigenvectors, V1, V2, Vn. Okay? So if you create the matrix of eigenvectors, then S inverse times AS is going to be your diagonal matrix. And that's going to be the diagonal matrix that has all the eigenvalues there. Okay, remember this right here, I just don't want us to be confused. This is just a matrix with eigenvectors as columns. Okay, so this is the key. The key is that if you take the eigenvectors and make them the columns of your matrix, then if you multiply S inverse times A times S, you get a diagonal matrix, and that's going to be all the eigenvalues in the diagonal. Okay, so this theorem actually has a very simple proof. So let's do the proof really quick. So let's start off with S inverse AS equals D. Okay, what does that imply? This is true if and only if AS is equal to SD, right? All I'm doing here is multiplying both sides on the left by S of the above, and I get AS is equal to SD. Okay? So what does this equal? So what does the left equal? The left is A times V1 to Vn. And this is equal to the matrix. Let me write it this way. I don't like the way I wrote this because I should put a beginning and an end to this. So these are columns, right? Each of these becomes a column. But then what are each of these? Well, let me leave these alone because I want to go on this side and then we will see that these are actually exactly the same thing. S times D is going to be what? It's going to be S, remember, is V1 to Vn. And this is going to be multiplied by the diagonal matrix, right? So it's going to be lambda 1, lambda 2, all the way to lambda n with a bunch of zeros here. Okay, what happens if you multiply these together? This becomes lambda 1 V1 lambda I Vi lambda n Vn. Okay, and I hope that everybody could see that these two guys have to be the same. Why? Because, recall, this is what it means to be an eigenvector, right? Isn't A times Vi equal to lambda I Vi for all I? Okay, so the left and right are clearly the same. Okay. So this leads us to a definition. Oh, that's the end of the proof. So this leads us to a definition. An n by n matrix that is similar to a diagonal matrix is called diagonalizable. So note, what does the last theorem that we just wrote down say? The theorem says A is diagonalizable if and only if A is, oh, you know what? I'm running low on space here. Let me back up a bit. I'm going to write it on the next line. A is diagonalizable if and only if A is non-defective. Okay, so this is what the theorem says. The theorem says that if A is a non-defective matrix, remember what that means. It means it has n linearly independent eigenvectors. It has as many eigenvectors as it does, dimension, n by n matrix. Then that means that it is diagonalizable. Okay? So, this is just really just adding terminology, and now we know how to diagonalize it, right? We just need to find the eigenvectors and then make those the columns of our matrix. So let's do an example. We're going to verify that A, which is matrix 3, -3, 3, -2, -2, 6, -2, -6, 10. Verify that that guy is diagonalizable. And find S such that S inverse AS is diagonal. Okay, so what do we need to do? So to show that A is diagonalizable, we need to show that A is non-defective, i.e. A has 3 linearly independent eigenvectors. This is what we need to show, okay? We don't know this yet, but that's what we need to show. Okay? So what is P of lambda equal to? Remember, this is going to be the determinant of, you take away lambda from the diagonals, 3 minus lambda, -2 minus lambda, 10 minus lambda, and then everything else stays the same. Okay, so if we do this, what we end up with, I'm going to go ahead and expand on the top row here. So if we expand on the top row, we end up with 3 minus lambda times, what do we get here? We get lambda squared minus 8 lambda minus 20, and then plus 36, and then plus 2 times -30 plus 3 lambda plus 18, and then minus 2 times -18 plus 6 plus 3 lambda. Okay, so what happens here? I'm going to simplify what's inside. Oh, I have to put this in parentheses. So what I have here is I have 3 minus lambda. If I combine like terms in here, I get lambda squared minus 8 lambda plus 16, and then plus 2 times 3 lambda minus 12, and then minus 2 times 3 lambda minus 12. Okay. Now, I'm hoping that you guys notice that because there's a 3 minus lambda here, I'm going to check to see if there's a 3 minus lambda in the others, but I do not have a 3 minus lambda in the others. So I'm going to go ahead and factor the left all the way. Now, normally you wouldn't do this, but we're doing this so that we can actually factor by grouping so we don't make this too complicated. You want to avoid getting a cubic because you can't factor that. So how do you factor this? We have 3 minus lambda, and then this guy is actually a perfect square. This is lambda minus 4 squared. And now we notice that if I pull a 3 out of this guy, I'm also going to have a lambda minus 4. So let me pull out a 3. So I get plus 6 times lambda minus 4. And then on this guy, I can pull out another 3. That's going to give me a minus 6. And I have a lambda minus 4. Now, all three have a lambda minus 4, but even better, these two terms cancel out. And so we are done factoring. This is actually equal to 3 minus lambda times lambda minus 4 squared. So I'm just going to pull out the negative just to make this look a little nicer. So this is equal to, let me write it over here again. So the characteristic polynomial is equal to, if you pull out a negative sign, you get lambda minus 3 times lambda minus 4 squared. And so we've got two eigenvalues. We've got lambda 1, which is 3, and lambda 2, which is 4. So let's find the eigenvector for the linearly independent eigenvectors for each one. Okay, so first let's do lambda 1 equals 3. We're going to do a minus 3I augmented. This is equal to 0, negative 3, 3, negative 2, 5, 6, negative 5, and then negative 2, negative 6, 7, and then 0, 0, 0, right? So this is what we get, and I have done the work in advance. I want to skip some steps here. We end up with the following matrix in row echelon form: 1, 0, 1/3, 0, 1, 1, 0, 0, 0, and then 0, 0, 0. So where's our free variable? Our free variable has to be right there. So this means x3 is equal to t, x2 is negative t, and x1 is equal to negative 1/3 t. So we end up with t times negative 1/3, negative 1, 1. By the way, this is the same as t times. Now, what I'm going to do is actually multiply this whole thing by negative 3, and I get 1, 3, negative 3. Why am I allowed to do that? Because remember, any scalar multiple is fine, so I just got rid of the fractions, okay? So my linearly independent eigenvectors for this eigenvalue, I just have 1, right? 1, 3, negative 3. So I'm going to call this guy V1. Okay, now let's do the second one. Lambda 2 is equal to 4. What is a minus 4I augmented? So this gives me the following matrix: negative 1, negative 3, 3, negative 2, negative 6, 6, negative 2, negative 6, 6, and then 0, 0, 0, right? Again, I've done the work in advance, and I end up with, actually this work is easy to do because the rows 2 and 3 are both scalar multiples of the first row. So you end up with 1, 2, 2, 0, and then the rest is all 0. So we actually need two free variables here, one here and one here. So we're going to write x3 is t, x2 is s, and then x1 would be negative 2s minus 2t. So what does this look like? This looks like t, or let me write it as s first. We get s times negative 2 1, 0 plus t times negative 2, 0, 1. Okay, so we actually have two linearly independent eigenvectors. I'm going to call this V2. V2 is negative 2, 1, 0, and V3 is equal to negative 2, 0, 1. Okay, these are two linearly independent eigenvectors. Okay, so all together, how many do we have? So all together, we have 3 linearly independent eigenvectors. And let's write them down. Okay, for lambda 1 is equal to 3, we had our eigenvector, we called it 1, 3, negative 3. Okay, and for lambda 2 is equal to 4, we had V2 equals negative 2, 0, 1, and V3 is equal to negative 2, 1, 0. So because we have 3 linearly independent eigenvectors, A is non-defective. Which means that A is diagonalizable. So how do you diagonalize it? Well, we're going to let S be. All you do is put the 3 eigenvectors as columns of S. And so we end up with 1, 3, negative 3, negative 2, 0, 1, negative 2, 1, 0. Okay, so this is S. And what does S inverse times A times S have to equal? It has to give us the eigenvalues and in the order that we listed the matrix, right? So because we listed it in the order with eigenvalue 3 and then 4, right? This is for lambda 1 and then lambda 2. It's got to go in that order. So when you actually diagonalize it, it's going to look like this: 3, 4, 4. Okay, I am not going to verify this, but if you wanted to, you could find the inverse of S. We know that that takes work, right? But you could find the inverse of this matrix S and then multiply S inverse times AS, and you will get this diagonal matrix. So this will be the diagonal matrix that is similar to A. Okay? Thank you very much for watching. That's it for this section.